So this neutron walks into a bar, orders a beer. Bartender brings him the beer, sets it down. Neutron says, "Thanks. How much do I owe you?" Bartender looks at the neutron and says, "Buddy, for you, no charge." Speaking of charges, last time we were talking about the hydrogen bonds and the polar nature of water, and we did the demonstration, and some of you watched the video, and it talked about how all the Mickey Mouse heads would be orienting themselves towards the charged object. In the case of our demonstration, it was a piece of PVC pipe. So here's the stream of water, and here's the negatively charged object that's nearby. If that negatively charged object wasn't there, you would expect these water molecules to sort of be randomly oriented in all different directions in the stream of water. But when that charged object is put nearby, it induces those water molecules to reorient themselves with their positive hydrogen sides facing the negatively charged object, and the stream bends with that electrical attraction between the positive and the negative charges. Cool stuff. Okay, for the chemistry experts in the class, and I know we apparently have some of that, that's cool. You can pause and read over this. This should be some review for you, and if it's not, don't worry too much about it. pH is a really important conceptual idea. The big deal here, as I've pointed out in the second bullet, is that pH is really important because of the way proteins are sensitive to changes in pH. The very precise three-dimensional structures of proteins that are essential, those structures, for the functioning of the protein, those structures, those shapes can change with changes in pH in the environment. And it has to do with the nature of the weak chemical attractions that hold together the structure of a protein. And changes in pH means change in the chemical environment. And so that can affect the shape of the protein and make it not function as well as it is supposed to, or not at all. And that's bad if you're a living thing, because we depend on our proteins to do most of the work inside of our cells. So you can pause this and take a look at it. The couple of key things to know: pH is a logarithmic scale, so if the pH goes up or down by 1 point, it's really a 10 times difference in the concentration of acid. And it is the concentration of these H+ ions, those are protons, that determine the acidity of the solution. The higher the concentration of the hydrogen ions, the greater the acidity, and because it's a negative logarithmic scale, the lower the pH would be. So if the concentration in moles of hydrogen ions per liter is 1 mole per liter, and if you don't know about moles yet, relax, it's just a measure of concentration. So that 1.0 concentration is equal to 10 to the 0. pH is a negative logarithmic scale, so the negative log of 10 to the 0 is 0. If the concentration is 0.001, which is 10 to the negative 3, a much lower concentration of the acid ions, so the pH goes up. And in fact, the pH goes, for example, from 4 to 7. You think that's 3 pH points, but if you look at the difference in the concentration, it's 1,000 times difference in the concentration of the ions. So that's why pH is important, because it denatures proteins, it changes their shapes, and we can't really live without our proteins doing their job. All right, single and double covalent bonds. We talked last time about covalent bonds being the mutual attraction between two atoms and the electrons that they share. And we see two similar molecules here that have all single covalent bonds in the case of the ethane on the left, And then the ethene has a single double covalent bond. A single double, that doesn't sound right. It has one double covalent bond between the two carbon atoms. And you can see from the diagram there's 4 electrons represented in that bond. And if you think about that definition we talked about last time, the covalent bond is the mutual attraction between the two atoms and the electrons that they share. If these two positively charged nuclei in the two carbon atoms are attracted to a cloud of 4 shared electrons, then that's going to be a stronger attraction than the ethane single bond, where there's only 2 electrons attracting those 2 nuclei to one another. So double covalent bonds are stronger, and they pull the 2 bonding atoms closer together than what we see with single covalent bonds. So a double covalent bond is a stronger bond than a single covalent bond. It takes more energy to break a bond like that, more difficult to break a bond like that, and more energy is released when a double bond is formed. Shapes of organic molecules. Chains of carbon, which are the backbones of all organic molecules, can take just about any shape you can imagine. And when we look at the two-dimensional diagrams of a chain of carbon atoms, like the hexane that's represented at the top here, it just looks like a straight line in that two-dimensional form. But in fact, it's not straight at all, because the bond angles between the carbon atoms and whatever atoms they're bonded to are really about 107 degrees. And so it's not a straight chain, it's a zigzag chain. And the bonded atoms, the things that are attached to the carbons, can in fact rotate around that carbon bond. They're not locked in position. So I've shown you the ball and stick models for a straight chain glucose molecule at the top here, and what is the more common version of glucose, a cyclic molecule, down below. So this straight chain is folded back on itself, a bond has formed to close that into a ring structure, and lots of organic molecules form one of these cyclic structures. If the cyclic structure in an organic molecule has alternating single bonds and double covalent bonds, then they call that an aromatic ring. And it's called aromatic because benzene and lots of the chemical compounds that are related to it have very distinctive smells. Functional groups in organic molecules. This is one of those things that is unlikely to come up in a bunch of questions that you're going to see on a test for physiology, but certainly might come up on tests that you may have as a biochemistry student or an organic chemistry student. Organic molecules are basically carbon and hydrogen and oxygen, but depending on the other possible elements that could be bonded to a chain of carbon atoms, those different elements and different configurations of carbon, oxygen, and hydrogen can give the molecules a distinctive character, a distinctive chemical character. And so this is showing you a couple of the important functional groups that can attach to a chain of carbon atoms. And I'm going to point out 4 of them that I think are important for you to know. And if I'm going to ask you about one, it's going to be one of these 4. And those are hydroxyl groups, the OH bonded to one of the carbons in the chain. And when you have a hydroxyl group bonded somewhere along the chain, that causes that molecule to become an alcohol. So all of the alcohols have OH groups attached to them somewhere. Aminos have NH2s or depending on how they're bonded, it's possible for that to be an NH group sticking off of the carbon chain. You know probably about amino acids. Amino acids have an amino group off one end of the molecule, and they have a carboxyl group, the third of the fourth that I think you ought to know, at the other end of the molecule. So amino groups are NH or NH2, and carboxyl groups are a carbon double bonded to one oxygen atom and single bonded to an OH at the end of the molecule. It has to be at the end for this to be a carboxyl group. And carboxyl groups are really important because these are organic acids. Like I said, amino acids have an amino group at one side and a carboxyl group on the other, and so that's why we call them amino acids. And then the last one, a phosphate group. Phosphate group is a phosphorus atom bonded to 4 oxygens, and depending on the chemical environment, there may be 1 or 2 hydrogens bonded to the oxygens. It depends on what else is going on in the chemical environment. And we'll find out that phosphate groups being transferred from one molecule to another is an important chemical messaging system in the cell, and it's also responsible for a lot of the energy usage in cells. All right, so I'm going to try to very quickly give an overview of the 4 different classes of organic molecules. Probably this is review for a lot of you. And again, I'm going to go quickly, and I'm going to depend on you all pausing the video, going into the book if you need to, looking things up, and asking me questions if you need to, because I don't want to go on and on about stuff that you may have already learned. Okay, so carbohydrates come from, the word carbohydrate comes from the combination of carbon, and hydrate, water. Carbohydrates have the general molecular formula of 1 carbon for every H2O. So for every carbon, there tends to be 2 hydrogens and 1 oxygen, more or less. So our carbohydrate is carbon per hydrate, or water, right? And we see some examples of the 2 important categories of carbohydrates here. Simple sugars in the shaded region on the left. And then if we bind a whole bunch of those simple sugars together, we get complex carbohydrates, polysaccharides. A saccharide is a sugar, and polysaccharides can be structural molecules like the cell walls of plants, and they can also be energy storage molecules like starch in plants and glycogen in animals like us. And mainly, carbohydrates are important for energy usage in cells. This shows the type of chemical reaction that is responsible for the formation of a complex of sugars. So if we want to put more than 1 sugar together in the cell, we do what is called a dehydration synthesis reaction, and it is called dehydration synthesis because a water molecule is removed from the collective 2 sugars that bond together, and where those 2 hydrogen and 1 oxygen atom depart, that's where the new chemical bond is formed between the 2 adjacent sugars to make a disaccharide. In this case, glucose is bonded to another glucose to make the disaccharide maltose, and a water molecule is released. The second diagram shows the more common table sugar, which is 1 glucose and 1 fructose bonded together by dehydration synthesis, and we wind up with sucrose, which is table sugar. If you add another and another and another simple sugar, monosaccharide, to this chain, you wind up getting a polysaccharide. So this is how those big complex carbohydrates are made. Just keep doing dehydration synthesis reactions to add 1 more, 1 more, 1 more. When we want to break down some stored carbohydrate and use it for energy, then we do a reaction that looks basically the opposite of the one that we just looked at. Now, instead of a water molecule being one of the products of the reaction, a water molecule is one of the reactants. It's necessary for the reaction to take place. So the water molecule plus some oligo or polysaccharide, some number of sugars bonded together. The water molecule, with the help of an enzyme, will break the chemical bond between two of the sugar residues, and those 2 hydrogen and 1 oxygen atoms will bond to the ends of the molecules where they have just been split apart. And that is called a hydrolysis reaction. Hydro, water, and lysis means splitting. So we're splitting an organic molecule into 2 using water. And those 2 types of reactions that we just went over, dehydration synthesis and hydrolysis, those are the 2 core reactions that are responsible for building up large, complex organic molecules and for breaking down large, complex organic molecules.